Okay. Let's continue. Let's see. I have 3 general topics today. I haven't even decided whether they're some are more tedious and some are more fun. Maybe we should start with what's fun first, and then go to the tedious. So I guess let's start with this is the advertised problem. So maybe you've looked on the there was some on the web page. There was one of the first links was to a sample entertainment. So one problem I want to talk about, I guess, and I might as well start with that now, is the Monty Hall quiz program problem. So we might this is hard not to have an opinion about. But if you try, I guess if you try hard, you cannot have an opinion. So instead of being here in the classroom, you're on a quiz show, and there are 3 doors. The 3 doors, and they're closed, and you're told that there's a new car behind one door and a goat behind each of the other 2 doors. And you get to pick a door. Well, that sounds pretty good. You can't go wrong there. You might have to figure out what to do with the goat if you get it. But okay, so you have to pick one of these doors, and that's just the beginning, though. So somehow or other, you pick this door. Right? That's the first stage. You pick this door. Whatever. By some means, you pick one of the doors. Let's say this one. Now the host comes, and after you've done this, the host opens this door and shows you behind this door the goat. Right? So you see there's a goat behind this door. And then he says to you, he wants to give you a deal. Do you want to change your choice? Would you like to change your choice from this one to this one? And the question is, what would you do? And is it to your advantage to change your choice? Somebody has an opinion. At least that causes a little quiet utterance in the room. Here you are. There's a goat here, right? Somebody said, I think, if I heard my antenna were getting some reaction, doesn't matter. Did somebody hear a kind of subliminal response? Doesn't matter, right? So, I don't know. Does somebody want to articulate that view? I mean, there's a car there, right? Behind one of these doors is a car. That part of it's supposed to be up front. You're supposed to be correct. There's a car behind one door, goats behind the other 2. You really would prefer the car a whole lot more than the goat. I don't know, that's not automatic, but and you've done this. You pick this door, and you're given the choice to switch. So how do you think about that? That's kind of in part. This is in part what this course is about. It's in part thinking about how would you think about this? What are the advantages? What's the probability? If you don't switch, what's your chance of winning? And if you do switch, what's your chance of winning? Or does it make any difference? Or should you switch or not? I see a hand. Yes. Thank you.
You should switch, and if you do switch, your probability will be 2/3. If you don't, probability will be 1/3.
Okay, should switch with confidence. And winning probability. No, okay, yes. Okay, one. Should not switch. Why?
This one was this, and if we had the
car prevents this one, it would never open this. So there is no car prevents this door. Like.
Well, let's see. So here where you pick this, he could have opened. This might be the car here, and there might be goats behind both of them. No, you can't. Well, now I didn't actually say what he could do, right? But presumably he isn't going to open your door, because if he opened your door and showed you the goat and offered you to switch, clearly you'd switch. If he showed you the car, you wouldn't switch. So he's opening. You picked a door, one of them, and he opens one of the other two doors, and he shows you a goat. He knows what's behind all the doors. So surely, whatever door you pick, whether there's a car here or a goat here, he can open another door with a goat. He wants to, right? So there's a door available. But we don't know whether, given the information now, right, initially there were 3 doors. The car could be behind any of the 3 doors without getting too fancy. Now he opened this door. We know that the car is not here. The car is behind one of these 2 doors. We've learned that, right? Yeah.
If you haven't picked the car, then his hand is forced to pick one of the doors.
Well, see, if you haven't picked the car, you picked a goat. Then, if you picked a goat, right? If he's going to open a door, if you pick the goat, but you'll have to pick. He'll be forced, yeah. If he opens the door, yeah. So what does that mean? We have a vote here, a vote for this liking this way. There's
and a 1/3 chance that the one that you already picked has the car.
Well, are there any other anybody have any other thoughts about this? Yeah, Michael.
You could look at two completely separate scenarios. You could look at the first one where we say 3 doors, pick one, you have 1/3 of a chance of winning the car. And then he eliminates one choice, and if you switch them, well, it's not, I don't think they're entirely unrelated problems, but then you have a 1/2 chance of winning the car, because there are 2 doors left. And so you're better off switching.
In some sense, if this door isn't here and you're looking at this, there's 2 doors left, you're thinking 50-50. Whereas you had 1/3 to begin with. Well, if he's going to open it's sort of like, so to start with, 1/3. For sure, right? They sort of say 3 doors, pick one. If you don't mess around, you win with probably 1/3. That's sort of clear, right? Then, at the end, if you don't mess around, it sort of looks like this, right? Because in the end, you have to pick these 2 doors. If you forget all the history, forget all the funny business, you're told you get to change. So you can pick either of these 2 doors, right? So there's, in some sense, right? You're right here. Sasha. So let me try to describe the problem again. I think we're at a point where I should word the problem very carefully. Let me word the problem very carefully and repeat the problem. You're on this game show. You're told truthfully that there's 3 doors and there's a car behind one door and a goat behind the other 2 doors, each of the other 2 doors. So there's 3 doors, there's goats behind 2 of them and a car behind one. You're told, pick a door and you're going to win, pick a door. And, if you pick the right door, you're going to get what's behind the door you pick. So you pick a door. The host of the game show, originally Monty Hall, comes to you and comes and opens this door, one of these other doors, and shows you a goat. And then he says, do you want to switch? I'm going to give you the opportunity to switch. Okay, Sasha.
If
car only has two doors. Pick one. Right?
Looks better, right? Start 1/3, end 1/2. Looks better. Yeah? Yeah?
Door, that has been improved to 1/2. For the goat, the initial probability was 2/3, but now it's still, the probability still remains 2/3.
Yes, so this was 1/3.
Right.
And now, he did, in some way, it doesn't matter what he did, right? This is always 1/3. But then at the end, it's now 1/2, sort of. I mean, actually, at the end, you're sitting here at the end, and you could pick one of these two doors. So 1/2 seems like, certainly at this point, you come in and say, pick one of these two doors. That's the choice, right? 1/2. Is there anything else, any issue here? I mean, the issue is, this is kind of an odd, there's an issue here that's extremely important. The issue has to do with learning about, like, this class. Like when I give you some question, on an exam, and it's sort of stated in some stupid, half-formulated way, and you've learned from experience how to make sense of it. So in some sense, maybe yeah, okay, I think there's maybe some more comments is good.
I'm not entirely sure if the two events are unrelated, but I don't think that you would enjoy the improvement to 1/2 odds if you don't switch. I think you're better off switching in the last stage.
Okay. Well, one of the things, let me try to switch the thought as, this is a little bit like the Blink book that I mentioned last time, of one part of this is how do you feel? I mean, now the thought is, how would you feel? Can you relate to this? There's a couple of ways of relating to this, and one way is to imagine that you really are on the game show. Now, this, okay, so you're on the game show, and you actually want the car, and you're thinking about this, and this happens. You don't go on game shows a lot. Let me start with that. You just, I mean, you're a serious student. You don't mess around. But you happen to go to the game show. You happen to be downtown. They happen to say, come on in, right next to the studio. And they said, come on in. And you think, gee, okay. And then here we are. We select you in the audience. And you go to the audience. And then there you are. And you're playing this game show. And the host says this to you. And you don't know quite what to expect. So do you have any attitude about it? I mean, imagine, wouldn't you, I mean, I'm just inviting that you might have some sort of feeling about the thing. I mean, you're there. Somebody says, you did this, you picked that. Doesn't it, you could, it seems like you could have an emotional response. See, you don't expect me to be concerned with emotional response. You expect, sort of correctly, you see, it's like the fox seeing the turkey and it's on the pan, all roasted and stuff. I mean, and you see me here, and you see me as the professor and sort of mathematician, and you translate what you already have in your mind what I'm concerned about. And you're already saying, we're going to clean, he must mean something sensible. I'm just trying to invite you to think about what you would feel. That's emotional response. How would you feel about this? Aren't there some reaction? So what would there be to feel about? I mean, I would feel something. I would have, and there's actually two very natural feelings that you'd have about whether this was a good idea. Yeah.
If he wants to make a deal with me, probably I was right, because he starts, give me like.
That's what I'm looking for. This is what I'm looking for. The host, what is he up to, right? What is he up to? So this is where there's two kinds of responses, which is, I would say that's the dominant, I would say that's the total reasonable response if you didn't think I was a professor asking you a math question. You'd say, what the hell's the guy thinking? What's he trying to do? Is he trying to trick me? I must have picked the car and he's trying to psych me out. Isn't that a totally reasonable response? I mean, not this math stuff, but what's the guy thinking? What's the host thinking, right? Isn't that what you'd really think? I mean, I pick this door, and he says, opens the other one, and says, you want to switch? You're thinking, what is he doing a mind job on me? What's going on, right? Wouldn't you think that? It's only because this is a course you wouldn't think that. You know that I shouldn't be asking you that. It should be a clean question I'm asking you, right? Yeah. Yeah, we never said a word about what he did in the past. You assume that he would always open the door because that's the clean math question. Not me, you assume, right? You assume that he would always do this. That's because this is a math, engineering/math class, and of course we're talking about math, and therefore, anything else that would sensible is irrelevant, right? Any sensible thing that you'd actually feel and think about is irrelevant, right? So when the past, in particular when I restated it, I did not say that he always opens the door. I said in this instance he opens the door, right? So what did he do in the past would help. I kind of tried to help you there by saying you didn't go very often, so maybe you don't know what he did in the past. But then you might have an opinion of what he's trying to do. Like if this was some deal on the street and somebody said, like what's under the 3 shells, and you watch and you follow, you say, geez, I can see just where they are, right? Where the thing is under the shells. Okay, and then, well, I mean, this is half of this problem. And this is half of a lot of problems, maybe more than half of problems, is the reality of the problem there's a lot of context that you don't often consider. And this has that. And that's actually worth considering. And your emotional response would be different from the math analysis, I think, right? I think you would reasonably think. Now, actually, there's a Rorschach test about how your attitude to the world in this response. I mean, I would guess that, 80% of us, or 80% of the time, we might be concerned that the guy's trying to trick us. That's a reasonable response. We pick the car, he's trying to psych us out to get us to change the choice. That's because he might not always do this. So let me just to emphasize 2 different things the host could do. The host could do this. He could open the door only when you pick the car. Right? Suppose the game show host strategy is to do nothing unless you pick the car, and when you pick the car, he gives you an opportunity to give it away. You have, in that policy, you can only lose. You should never shift, right? You had 1/3, but if he's out to get you, he's just anything you do is going to cost you. On the other hand, there's another view that comes from watching game shows enough. I guess my 15-year-old actually responded this way, and I thought it was pretty good. I thought it was very positive. It's the opposite response. So then he says to me, I'd shift. But he isn't bothered, he isn't in probability, and he isn't bothered by trying to math formulate it. He just takes the thing straight away. It's like a game show. He's seen game shows. But his response was, and I think this is perhaps is valid, actually, for what I know about game shows. I don't know how they've changed over time. My watching of game shows has somewhat declined over time. But at any rate, his response was, the guy wants me to win. He's trying to help me. People like to see you win. So he's helping, he's trying to help me win. I mean, this is an attitude, right? I mean, either it's an opposite attitude, totally extreme. So if you think other people, if you think the guy's trying to help you, you think, oh, he's offering me an opportunity, right? It's totally within his power. He could have, if he wants you to lose, he offers you to change only when the car is here. On the other hand, if he wants you to win, you're guaranteed to win if he has that attitude, because he only offers you the change when the car is here. And then, in that view, you always win if you change. So that given that the host wants you to lose, change is guaranteed to lose. Given that he wants you to win, change is guaranteed to win. Yeah.
Probability problem. So, let A be the event that the door you pick has a car initially, and then let B be the event that at least one of the other doors is empty. So
So you calculate the probability of B given A, which is 1/3, and then 1 minus that would be the probability that you win if you switch.
So we're getting back to here, and I'll come back to this. And I guess the point I'm trying to make is that's not the point. The point I'm trying to make is there is a problem there that's exactly like that. And I spend my whole life doing that. And it's just good to be aware that the host's motives are at issue. We haven't formulated what they are. And if you think the guy's out to get you, you're not going to want to switch. And if you think the guy's going to help you, you will switch, right? Doesn't that? And if he doesn't do the same thing all the time, isn't that? I mean, I'm just saying there's no math that's going to get around that. If he's out to help you and only offers, suppose it was your best friend who's doing this, and you know that you can count on him only to offer the change when the thing's there. Then, you know, when he offers you, you're going to do it for sure, right? I mean, it's, yeah. Yeah. This means you're like in this course. 99.999% of the time, all our questions are going to have a natural mathematical formulation, which is we all naturally gravitate to. There's a certain sense in which it's natural for us to view this problem in a clean mathematical way. So in particular, I'm just saying I want to bring to mind, before you sink into the math, that there are other issues. But in fact, it's perfectly natural to be interested in the math, the clean math problem. You say, okay, forget that stuff. Suppose you say that the assumption that's missing, but we're all sort of implicitly making, usually, in this problem, the assumption is that the host will always open a door. Every time you pick some door, he'll open the door. One of the other doors, there's necessarily one with a goat. If there's only one with a goat, he opens that. If there's two, he picks it somehow, one of them. And the assumption, a different problem is, suppose the game show host always opens a door, like a machine, exactly what you said. And that's the clean problem, right? That's the clean problem, and it's worth thinking about that. I just want to emphasize at first that there are issues that aren't like that, and they may be important, right? So you could take, now when you come, that's an implicit assumption. I was just emphasizing that in the beginning, I did not assume that the host was going to always open the door. I didn't say that, right? That was not stated, deliberately not stated. But the natural thing to think is, well, of course, this is supposed to be a well-defined math problem that's going to be clean to think about, right? So if we make that assumption, it's reasonable. So let's make that assumption. So the assumption is, every time you play this game, he's going to open a door. And he's going to open a door with a goat. I mean, he's not going to open the car. So he's going to show you a goat, okay? And then you are stuck with this problem. And now you still have a problem to think about what the probability is, right? I mean, this is just back to where we started. I just made a diversion. I'm trying to emphasize that there can be non-mathematical issues that are more important than the math. But once you say, okay, he's going to open a door every time, you're left to think about this stuff, all of this, right? You're back here again. And your model of can't you do this as conditional probability is, I mean, then it's the guy's acting like a machine. That's exactly what you want to do, right? You want to think about this as conditional probability. Now, you can also take a view, once you think about this a while, you can take a view of explanation. You can look for an explanation that avoids careful, IUR 4106 thinking, but just try to do it in a way that persuades somebody. So I want to give you an argument that will persuade you without any math. Okay? No math. But this is sort of, this is counter to my usual approach would be just think, go slowly, do the math, figure it out. But there's actually, this problem is, so I would opt with this. Once we've assumed that the host acts like a machine and always opens a door, this is totally reasonable. But the way to think about it is, here's a way, I like this way. There are 3 doors. I'm going to give you, and initially you pick one and you got a 1/3 chance. But with this game, we're going to get a 2/3 chance. Because you decide in advance that you're going to switch. So you get to, instead of picking one door, you get to pick two doors. One door gives you 1/3 chance. You pick two doors. Okay? Right? Just imagine you just pick once. You get to, you're doing this at the beginning before the host says anything. But you know he's always going to tell you, open a door and so forth, right? So at the beginning, instead of picking one door, you pick two doors. So your chance of winning is 2/3. Now, how do you implement that? You pick this door and this door. Forget the guy doing this for the time being. You pick these two doors in advance, so your chance of winning is 2/3. But how do you play the game? Having picked these two doors as the ones you want to pick for your chances to win, you actually select this door. And when he opens one of the other doors and asks you if you want to switch, you always switch. So you will then get what's ever behind these two doors. Right? I mean, you just do the thing in reverse order. You pick two doors, your chance of winning is 2/3, but when you play the game, you open the third door and switch. So the door you first pick, is the one that you're not going to get. But whatever's behind the other two doors, you're going to get. 2/3. I mean, I avoided the probability trees. I mean, if you just think about it in reverse, because you're thinking the game's played and he's always going to open a door and it's always going to have a goat, because he's doing it like a machine, you could think about, at first, I'll pick these two doors, and the door, because I'm always going to switch. The two doors, I'm picking the third door and switching. So I've got the two doors. Okay, you may not be happy. This problem is wonderful. It appeared, it's got a long history, this Monty Hall quiz program. You can Google it. It's wonderful. When you Google the Monty Hall quiz program, I'll put some links there. See what's current now. You can find simulators. So one way to do this is to actually just do a simulation of this and see what happens when you do different things. And you'll see that you convince yourself if you don't switch, if you just always pick a door, your chance of winning is 1/3. If you always switch, your chance will be winning 2/3. You can just see it you can simulate it. But the best part is the discussion. And the part that you would like is, this was written up and somebody said like this. I guess this was Marilyn von Savant had some article about this problem, and she explained that you should switch. And then people would write in, and this caused a whole lot of controversy. People would write in and they would say, the star responses are, the starting point, the way to start the response is, I'm Professor Witt from Columbia, right? Let's see, that's not enough, maybe. I'm Professor Witt, and I have these degrees, and I've been going to school continuously since I was 4, and I have honorary degrees from these 7 schools, and therefore I want you to know this. This answer's all wrong, right? And that, right? Well, okay. So sort of like, people are laying out. What's great is that, and this is great. They're laying out all their, they want to say what an idiot the person is, and then they go, they start off by all their credentials and so forth. But anyway. Yeah, that's right. So this is an old problem. But there's all these people that interact. So it's totally reasonable. It's totally reasonable that you might still be not totally happy about this. Because at the time this went on, it went on back and forth, and there are websites about the thing. And so people are not totally happy. I hope that the issue of what you assume about the game host is, you can see it's absolutely critical. And then if you assume it acts like a machine, it's a little bit more of a problem. And anyway, I like my solution, but you might not now. So you can think about it. But the stuff online is good. There's actually somehow you can read the letters too. They saved some of these letters, but I like the stuff like I'm the professor, and therefore QED. regardless of any content, I'm right. Okay, well, that's this thing. And you could do, I don't want to beat it, I already beat it into the ground, so let's not, I won't start drawing probability trees to say how I could also do it that way. Okay, we're going downhill. We're going downhill from that. If that was bad, we're going downhill. I wanted to finish some of the stuff about conditional probability, and this is the theme of divide and conquer. So the problem I want to consider is a cards thing. So you're calculating some probabilities of events when you're for a deck of cards. And you want to know you have I hope you all know what a deck of cards is. You have 52 cards, 4 suits. You in this instance you deal out 4 hands of 13 cards each. Like you're going to play bridge, so there's 52 cards, and then you have 4 hands of 13 cards each, and there's you want to know, so the event you're interested in, this E event, 1 ace in each hand. So there's ace, king, queen, jack, so forth, 10, 9, down to 2. There's 13 cards, 4 suits, and you want to know, and so you've dealt out the cards randomly. They're well shuffled, 52 cards. You dealt 4 hands of 13 cards, and you don't want to know the probability that there's exactly 1 ace in each of the 4 hands, because there's 4 aces in total, and you want to know that probability. Now, the approach is to, this doesn't have any conditional probability in it, right? There isn't any conditional probability. And an approach to this problem is to break it up into pieces and attack it by this divide and conquer. So what I want to emphasize is you could be deliberately introducing conditional probability in order to simplify the problem. It's a kind of technique that you're saying, I want to do something, I want to calculate a probability, but and it's just a straightforward question, but if you actually proceed in a kind of break it up into pieces, it's going to be easier to analyze. So this is the thing, and one way is EI is 1 ace in hand I. And so now you've made events I equals 1, 2, 3, 4. So you've introduced 4 new events to get at this. And so E equals, that's right. So the event we're interested in is that there's 1 ace in each hand, and this says there's 1 ace in hand I. So the intersection of those 4 new events is the one we care about. And that sort of the idea was to introduce these artificially as a way to get at the thing we want. And I'm sort of emphasizing this, which is in every course we do in IEOR when it's problem solving. This is probably a standard technique. One way or another is to break the problem up into pieces and solve it. And so this is an example of that. And the thing you want to do then is, okay, you want to know this by above. Okay, so the idea is start one at a time. So what we're going to do is the probability of E1. So we'll just look at one of these individual events, and then the probability of E2 given E1, and then the probability of E3 given E1 and E2, and then the probability of E4 given E1, E2, and E3. Right? So this is sort of a natural step. I mean, I've made 4 events, and I want to know about the intersection, the probability of the intersection. I find the probability of E1, so I've reduced it to one of these, and then I find the probability of E2 given E1, then the probability of E3 given those two, and so I made it 4 separate calculations instead of 1. Well, the first thing you want to see is this equation is correct in principle. I mean, that this is really the right thing. So let's just put the definitions down here. Let's see what this is. This is, by definition, and by definition, right? Because the conditional probability is the probability of the intersection divided by the probability of the conditioning event. So I'm just using the definition of conditional probability, right? I'm using this definition, which we went and used over and over again on Tuesday. So I'm using this definition for these funny events here that have got intersections in it. So I use that definition to replace that by this, and this by this, and this by this. Having done that, you see that this cancels, and this cancels, and sure enough, it's the right thing. So that ought to be clear that you could break things up this way. You know, if you want to calculate the probability of the intersection, you could do it in this way, in these 4 steps. And this is just checking that whenever you did this, the same idea would apply to any number of steps. If you want to calculate the probability of the intersection of a whole lot of events, you could do it one at a time with these conditions. I mean, and then you're left with the okay. We haven't done any conquering yet. We've done dividing. We've done a strategy of how we're dividing, but we need to do some calculation. And actually, these are problems in the book. So these are 26, 1.26, and 1.27. Both of these problems do this problem in this way. They only differ by what the events, the 4 events you define, E1, E2, E3, E4. So you can be more or less clever about choosing the right events that make the calculation go fast. That's Ross is very good at this. He's a master at doing this stuff in a clever way. When overdue, the direct way is all right. So at the same time, this first 2 weeks, the right response to this first 2 weeks, we're doing probability for 2 weeks. That's not really what this course is about. You're supposed to know this already. So the right attitude would be, if this seems totally new, you're in deep weeds. You're in trouble, and so you should work hard. Maybe you can still manage, but if what I'm talking about seems totally strange, you think I better really work hard, because it's going to be a challenge. If what I'm saying seems really easy, know that 2 weeks we're doing a review, and so don't think there's nothing. We're not doing stochastic processes for 2 weeks. We're just doing some probability. We're kind of getting warmed up, okay? But I mean, this stuff ought to be. Even so, this stuff is kind of hard. And actually, if you really have a hard time with this course, it's going to most likely be not because the stuff here is itself hard, It's because the stuff that you need to do routinely doing the problems here, you may not have learned as well as you should have. In other words, all this stuff is cumulative, right? So here you need to know probability to do stochastic processes, but you also need to know calculus and high school algebra and all this stuff. So you're going to have to integrate functions and do things that require calculus. So you want to know all sort of the math that you did before, linear algebra to some degree, and you want to know calculus and so forth and all that stuff, and especially basic probability like we're doing now is the part that usually causes the problem. If somehow that was too long ago in the past or whatever, that's going to be. So then the review of the probability or having that other book may be helpful and so forth. But otherwise, it's just we're getting back on. Okay, so then we want to do, if we're doing this, we want to do this. So if we start with probability 1 ace in the first hand, that ought to be sort of straightforward. And I'm thinking I would write this down, and I would I could get in trouble here, but so I'm counting now. So when I'm actually thinking of counting, and I'm doing probabilities by counting, so I'm counting the number of ways things can happen, and I 1 over the number of ways things can happen. So this 5213 is the number of ways I can select 13, deal a hand of 13 cards from a deck of 52. This is the number of different hands I could select. This is combination. So this is some kind of thing that you'd want to be knowing. All this stuff would be familiar somehow from wherever, high school math, 8th grade math, I don't know, something like this combination. Now, so let's think, actually, if we had to rethink that, so let's think about, this is the number of ways we can choose 4 items from 7. This is, I can write this down easier. I just want to check that this thing is 7 factorial over 4 factorial, 3 factorial. And how might we think of this? Just to review. You have 7 items. You want to know how many different ways can I select 4. So you might say, well, let's just first think about how many orders for 7. So you'd say, well, I can pick the first item 7 ways. And having done that, I can pick the next one 6, next one 5, next one 4, next one 3, 2. So this is the number of orders of 7 items. And then I'm thinking, oh, well, I'll put the first 4 in the first pile and the other 3 in the other. Right? So now I ordered them, this many 7 factorial orders, different ways to order them, and I put the first 4 in one group and the second 3 in the other. However, I've actually counted the different arrangements of these differently. I've counted them multiple times because if I changed the numbers, if I labeled them, the order of these is counted as different. So I want to actually discount by the number of ways I could order these 4 items and the number of ways I could order these. So I'm dividing by 4 factorial because there's 4 factorial orders of these items and 3 factorial order of these. So this is the number of ways I can pick 4 items from 7. And therefore, this is from this. And so here, what am I doing? I'm saying, well, this is the number of hands of size 13, and this is the number of ways I can allocate 1 ace from 4 and 12 other cards from the remaining 48. Counting. And that's probability. Okay, so that should be, that's this thing. Now, and well, okay, now this gets, here, you want to think that you've fixed 13 cards. The first 13 have been chosen, and there's an ace in there in the 13 cards. And so then you want to have, there's 3 aces left, and there's 36 other cards. Let's see if I got this right, 36. So there's overall, there's 39 cards left, and I'm going to take 13. And there's 3 aces and 36 other cards. And then if I do PE3 given E2, E1, both of these, I'm thinking 26 cards have been chosen. So there's 26 left, and I'm going to pick 13. There's 2 aces left. I'm going to pick 1. And there is 24 other cards left. I'm going to pick 12. So we're not really going to dwell on this a whole lot, but this is kind of one way to get that. And then having picked the others, you're all done. So P, E4, given E1, E2, E3 is 1. And now you've got all these factorials. I mean, this stuff is factorials. And if you cancel everything here, let me do it, put it here. If you do a lot of arithmetic, I'll spare you all the details. I think it goes, let's see if I'm getting it right, 39, 26, 13 over 51, 50, and 49. You have a lot of factorials, all this stuff. Remember, this thing is 48 factorial over 12 factorial, 36 factorial, this particular thing here. So when you have all these factorials and you write them all down and you cancel them all out, you get this as the answer. So you're doing arithmetic and algebra and stuff. You get this. So then this is where Ross does something nice. He actually finds a way to get this directly. I mean, if you think about the problem right and you approach it a little bit more carefully, you actually can be clever and have you define your events this way. So E1 is the ace of spades is in some hand. E2 is the ace of hearts, and the ace of spades are in different hands. And then E3 is the ace of diamonds, and these two is also different hand. And then E4 is the ace of clubs, is in a different hand. So then he's going to build up these hands. I guess let's do that here. So at first, it's a little different. At first, the ace of spades is necessarily in some hand. So with this new sets, the ace of spades is somewhere. So here's a hand. We've got a hand. There's 12 cards, and there's the ace of spades. There's this hand. And there's 13 cards here, and there's 39 cards over here. So now we're going to work on this probability E2, E1. So what we want to find out now is what's the probability that the ace of hearts is in a different hand. It's not in the same hand with the ace of spades. So these 12 cards are in the hand with the ace of spades, and these 39 are not. So you want the ace of hearts to be in here instead of here. So this, it's in the 39 instead of the 39 plus 12. Equals 39 over 51. Right? The ace of hearts is here instead of here in these unknown cards. Okay, then having done that, you now have ace of hearts and 12 more cards. So you now want to look at probability E3 given E1, E2. And now you're saying, well, there's 24 other cards, right? Or 26 other cards. So I want the ace of diamonds to be here instead of in these two groups of 12. So then I get 26 over 50. And you're getting, each of these steps produces this. Boom. Just, this is, I don't know, there's this the subject is full of tricks. If you think of the thing the right way, you can often be very fast. This sort of illustrates that. Perhaps it's not essential to know tricks. You can get along fine without knowing tricks. They're kind of fun, but you get along fine. It's more important to understand when assumptions are there, like in the problem about the quiz show, it's more important to realize not everything's math. This is fine. It's a trick you can get right there. Boom. Okay, not too important. Okay, how are we doing? We're in time to, we have time in the remaining portion of the class to learn the entire subject of statistics. Okay? Yes? Okay, so, well, this is a probabilist view of statistics. The point of statistics is, maybe a major point is to understand this stuff's going to be online. I wouldn't worry too much. I mean, some part of this is, I'll be putting some parts of a lot of what I do, like this problem, will be online, so you'll be able to see notes. Like there was notes from Tuesday, and I'll be doing some, so taking notes will probably not be too important. Okay, so we have about 15 minutes to do all of statistics. This is a prototypical problem. You have a document of unknown authorship, and I like this typical thing you're always reading about is somebody found another play, or a play not so much, but a sonnet by Shakespeare, right? And you find this document, and you know a lot about this author. Like, I guess the Federalist Papers are another thing, is like Madison and Hamilton. Who wrote this, these guys? Who wrote this kind of candidate document? And you already know that various authors have written a lot of other documents. So you know something about the author, and the author's you have a whole lot of documents the author's written, and you have some other document you want to know if that author also wrote that document. And, well, it's kind of complicated, and there's a lot of things you can do, and as you get more and more complicated, it's not clear. I'm not trying to suggest that I'm going to answer this in the best way. I'm just going to give you a way to get some insight. So in particular, we'll focus on the occurrence of one word in the document. You think, well, there's some word in the corpus, in the body of this author, then you know how often that word occurs, and then you compare that to this document in question. And the question is the idea sort of is knowing the known, so the known body of work. Okay, and then you have the unknown document. And sort of the point of view is, could this unknown document reasonably be written by this author who wrote this known body of work? And so the kind of thought is, so I had this European math friend who seemed to, he was Dutch, and he would always use the word bovendien in everything he said. So that in English is moreover. So I kind of like this. So moreover. And so maybe in his work there might be in 4 million words there would be 2,000 instances of moreover. Sort of the idea. It's written a lot. There's 4 million words, and there are 2,000 occurrences of moreover. I mean, this is, whether that's a lot or not, maybe that's crazy, that's too much. Then this unknown document has, say, 2 out of 4,000. Now, and then you think, well, this is sort of, an approach statistically is say, well, suppose this unknown document, it has 4,000 words. I mean, the kind of statistical assumption, which is almost as bad as the game show host, right, is that these are 4,000 words selected totally at random from maybe these 4 million words, right? And that, I mean, that doesn't quite make sense, because maybe the moreovers all occur in a clump. They don't occur at random, right? I mean, depending on what you're, certainly if it's some referring to some person, that person may be mentioned every few sentences in one place and not random. So this model is highly questionable, but well, there's more words you can do than just looking at one. You can be looking at a lot. But this is sort of just thinking about this. So we think, oh, there's this large body of work. So from this, we look at that and we see, well, the probability that each word would be moreover would be 2,000 over 4 million, right? And that's 2 over 4 is 1 over 200, right? Did I do 1 over 2,000? Let's make it more often. One out of 400,000. Now it's 1 over 200. So it's fairly often. So this is 0.005. This is 2 out of 4,000. This probability here is 1 over 2,000. So that's not quite the same. If it was the same, we'd have no reason to complain for sure, right? If the fraction of occurrence in the two instances, or if the proportion is the same, we wouldn't have proved. I mean, the point is, if they were both the same percentages, that wouldn't prove that it was the author, but it would be no reason to say it was any evidence against it. But now we've made this, we're saying here that 1 out of every 200 words is moreover. And we're now saying, suppose these 4,000 words are 4,000 words chosen at random, where each word is moreover with this probability. That's a model. And a model is not perfect by any means, right? Again, the model's not perfect, but that's a kind of statistical model. That's prototypical statistics. You're saying, when I want to know if this is different from that, I'm asking, say, well, suppose each word in here occurred at random with probability being moreover with this probability. What's the chance I would see something like this? That's the kind of spirit of statistics. You've made a model. This model may not be that great because things may be more clumpy. I'm assuming that each word, each of these 4,000 words is any of the words, possible words. In other words, in particular, each of these is moreover with probability 1/200, independent of everything else. That's kind of, I'm making a mathematical model. That's the point. I'm just trying to illustrate. I'm making a mathematical model to say I'm going to assume this. And now you say, well, what's the probability? What's the probability? This is now small. What's the probability that the number of those moreovers is less than or equal to 2, given this model? You know, if we took 4,000 words at random from this author, what's the probability we would observe less than or equal to 2 moreovers? And we're going to see if it's small, we're going to say, well, then it's not very likely. Okay, so then the part of this is to compute that, and we would see that this is exactly binomial. So binomial, well, it would be binomial less than or equal to 2, so it would be this, which would be the sum of the binomial k np, where k is equal to 0 up to 2, less than or equal to 2, and n in this binomial case is, let's see now, if I'm getting this right, the probability is 1 over 200. We're assuming that's the case, and the sample size is 4,000, right? Yeah. Now we've made it, I mean, the point now is, here, the thing, maybe it's obvious in a way, the expected number, the probability in the real thing is 1 over 200. The expected number in 4,000 is NP, So 4,000 over 200 is 20. Now that we've changed the units, right? So now the expected number we expect to see in 4,000 is 20, and we only see 2. So we, without getting involved in a whole lot of math, we now think things are not too good, that it's not very likely. That's the point. Before we even start crunching, right? In the whole thing, the proportion of words that are moreover is 1 over 200, and we would expect to see 20, and we only see 2. So then we're saying, okay, well, somehow we're saying the chance of seeing not just 2, any given number's got to be small no matter what, but the chance of seeing 2 or fewer. So that's where the probability, under that assumption, the probability of seeing less than or equal to 2 is going to be, I'm going to calculate it, and if that probability is very small, I'm going to say it's unlikely that this new document was written by that author. And it's the spirit of creating a probability model and looking and seeing how unlikely is the event you see. And if the event that you're thinking about is very unlikely, you conclude that that's probably didn't happen. Okay, so here we have this binomial. So this is one of the distributions we're learning. We're doing B, K, N, P. The probability of K, this is the probability that N equals K, and that's Nk, P to the K, 1 minus P to the N minus K. So here, that's 4,000 K, 1 over 200 to the K, 199 over 200 to the N minus K. And then we have to sum those up. Now, we're beginning to get to the point where there are some big ideas that the subject is not all tricks and minor technical details. We're beginning to get to a point where you could actually bring to bear some serious substance in probability. So this is the probability actually has something to say that's not just calculations. I mean, actually, maybe the subject of probability is calculating probabilities, but that's not just a numerical exercise. There's some ideas, major ideas about thinking about things that have to do with this problem. So you can compute all this, but it's kind of messy. As you can see, it's kind of big numbers. And the fact that when you see the thing as big numbers, maybe you might think that it would simplify somehow. And what I'm looking for is that you might be able to look at this and kind of make quick estimate. So you could actually look at this and see very quickly that this is unlikely. First of all, your intuition, if the mean is 20 and you're looking at 2, it doesn't look good. But you might also think about it more systematically. There's 2 kinds of approximations that are reasonable in this setting. One is the Poisson approximation for the binomial, which is in your first homework, and the other is the normal approximation for either the binomial or the Poisson. And those are amazing principles that simplify mess like this to a simple calculation. Let's just sort of, the high-level view, how you might think about this problem is the following thing. You would say, well, this is binomial, and the Poisson comes in when n is big and p is small. And in our case, this is overkill. This is certainly true. I mean, this is true in spades. So really, one on the card. This is true in a big way. So this thing's approximately Poisson. Now, the point of Poisson is you reduce these 2 parameters to 1. So you've reduced the problem, and actually then it looks like the 0 is e to the minus lambda plus e to the minus lambda lambda 1, just that, plus e to the minus lambda lambda squared over 2 factorial. So this is the probability that we would be computing. The sum of these probabilities for k equals 0, 1, and 2, if it's Poisson, would look like this. So it would be very fast to write down. And there's the Poisson approximation for the binomial, so you don't need to do 199 over 200 to the 3,999 power. This thing here, right, would be messy. I mean, just say this thing, if you had to do 3 of them, it's sort of, you'd be crunching away. It actually will be very accurate to this. Now, then, moreover, Poisson is approximately normal if lambda not small, not too small. Now, the lambda is just the mean. The mean here was 20. So 20 also is not too small. It's not, the mean is not like less than 1 or something. It's 20. So the mean actually is big. So then actually this number is approximately normal. Okay, so, and Poisson, the thing you'd know, this is how you would do this problem instantly, in less than 30 seconds when you first heard it. You would say, oh, well, it's binomial with mean 20, and I want to know if 2 is unlikely. But in this case, it's clearly Poisson with parameter 20. But Poisson has its mean and variance equal, so it's normal with mean equal variance. So it's normal with mean 20 and variance 20. It's normal with mean 20 and standard deviation square root of 20, which is about 4, right? 4 plus. So therefore, what you're going to see, 2 standard deviations is 20 plus or minus 8. 3 standard deviations is 20 plus or minus 12. 2 is way beyond that from 20. So right away you say no. You know, very high unlikely, like it's less than some very, very small thing because it's about 4 or 5 standard deviations away from the mean. And you could do that, you could reasonably do that instantly when somebody told you the problem. I mean, if you're walking into the warehouse, you're an IE person and you're evaluating some sort of inventory, and there may be an issue like this, and you could think quickly and see, oh yeah, this is this reasonable? And you could right away look and see here, oh, isn't it? Yeah, okay.
Make sure so Poisson is always approximated like with if lambda is big, normal lambda squared.
So this thing is Poisson lambda is approximately normal lambda. Mean and variance are equal. But standard deviation square root of lambda. So that's so the 20 is the mean, and the square root's the standard deviation, and things are going to be mostly within 2 standard deviations. So being between 10 and 30, you know, if it was from this, if you took a sample of 4,000 words from this big thing, and the probability was 1 over 200, you would expect to get 20 plus or minus 10. That's more than, you know, that you could be pretty sure that that's sort of like more than 2 standard deviations plus or minus 10. So the answers would be between 10 and 30. And once you go another to 2, or if you went to 40, you know, 38, it's way off target. It would be unlikely. There's plenty of reasons to complain. You'd say, well, really, this model doesn't fit. Okay, the model may not fit. That, on the other hand, at least it's an initial ballpark view that's actually may be sufficient in many cases, this kind of thinking. Right? I mean, many cases, things are not too far off, these models, simple models. The thing that's a little odd is you're thinking about this oscillates, as will oscillate maybe for the rest of your life, is at first it sort of seems, you don't think about it too much, but then so reach a point where you're actually surprised how well the model fits. But that you have to experience by actually, you experience that by actually applying the model in actual situations and seeing for yourself that it really tells the story. Because there's all these other issues that are extraneous. And the question is whether the analysis that you're doing really comes to the point. And in this instant, you can do it quickly. The point to emphasize, you got this thing that's binomial. It was a statistical question. It's easy to see it's approximately Poisson. It's easy to see it's approximately normal. It's easy to calculate the mean and variance. You instantly look at the mean plus so many standard deviations. Can't happen. I mean, and that ought to be, that's the kind of thinking, that's good thinking that you should absorb from this course rather than just computation. I mean, rather than, oh, I write this down and I compute it and I spend 15 minutes computing it. You're missing 90% of the story if you can't get to the answer instantly. You know, to think the right way and see that clear thinking makes you see it quickly, what's going on. I mean, because the error is not, you can check this point, the error is not in the accuracy of the approximation for this exact thing. The error in this problem, as in almost all applications, is not in the arithmetic in the approximations. The error is maybe the whole model doesn't fit that well. Considering the issue of whether the model fits, this error is in these approximations. Of course, it's good to check for yourself, but the error in the approximations is like nothing compared to whether the model fits. I mean, there's the question of how good is the normal for the Poisson, how good is the Poisson for the binomial. You can check that out. But it's those other issues that we're not checking that are often the big ones, right? Whether this model makes any sense. Okay, that seems to be, yes, excessive. Excessive by 1 minute on the other end. Okay, so you have, there's homework online, but with solutions online, which are due Tuesday.